Welcome to Module 1, Chapter 1.2, Introductions to Relations and Functions. We're going to use interval notation to write the solution sets for inequalities. So, for instance, we're used to doing x is greater than 4, and the graph would look like if you had a number line, there's 4 on the number line. Remember, greater than means it does not include 4. So instead of doing an open circle on the number line like we're used to, we're going to do a parenthesis on the number line to show that it does not include 4, and then we shade everything to the right. Now, interval notation, if you're not familiar with it, you write the interval that's being shaded on your number line. So if you read your number line from left to right, you come across, and the shading begins at 4, so you write 4, comma, the shading goes all the way out to the right, which we call that all the way to infinity, and then infinity ends with a parenthesis. Okay, let's do another one. If x is less than negative 9, let's change that to x is less than or equal to, just for a different problem. X is less than or equal to negative 9. You say, well, here's negative 9. Less than means we're shading back to the left. This time, because it's or equal to, it includes negative 9. So we put a bracket on negative 9. Now, interval notation says, where does the shading start as you read it from left to right? Well, when the graph goes forever and ever in the negative direction, we call that negative infinity. So we start out by saying negative infinity up to, and the graph shading ends at negative 9. It includes negative 9, so we put a bracket. Now, it does not matter whether it's less than or equal to, greater than or equal to. Infinities always get a parenthesis. Now, the last one, negative 3 is less than x is less than negative 1. You put the numbers on the number line. There's negative 3, there's negative 1. Negative 3 is less than x, which means x is greater than negative 3. Does not include negative 3, so we do a parenthesis and shade to the right. X is less than negative 1 means parenthesis on negative 1 going to the left. So we are going to shade all numbers between negative 3 and negative 1. Interval notation says we start shading at negative 3. We continue shading up until negative 1. And then we do a parenthesis. Now, this chart talks about the different types of interval notation. Now, something that may be new to you is this set builder notation. If we're used to writing x is greater than 4, set builder notation just says write it as the set of all x, where x is greater than 4. So that's not really a big deal. So if you see that, this piece inside the shaded inside the brackets, that's what tells us where to shade. Now, so if x is between two numbers, we put it in parentheses. This is called an open interval because it's the equivalent of both endpoints being open circles. The next one, x is between 2 and 5. This time, we call it a closed interval. That's the equivalent of using closed circles. But anytime we're dealing with interval notation, we use parentheses and brackets instead of open circles and closed circles. Then we can have half-open intervals. We have unbounded intervals. Anytime you see the graph go off to the right, you know it's infinity. Anytime you see the graph go off to the left, it's negative infinity. And anytime that the whole graph is shaded, we'll say it's all real numbers, and sometimes we'll use a little bolded R to denote all real numbers. Okay, now for definitions of relations and functions. A relation is a set of ordered pairs. If we denote the ordered pairs in the relation by x, comma, y, the set of all x values is called the domain, and the set of all y values is called the range. So for instance, in this one, let's say we let S be the set of ordered pairs 7, 3, 11, 8, 10, 1, and 10, 6. The domain is the set of x values, 7, 11, 10, and 10. Now when we write those, we don't have to write 10 twice because it's the same element. You can list it both, but you don't have to. The range is 3, 8, 1, and 6. Well, when you do those, it doesn't really matter which one you put first. You can list them in order that they're given or in order from smallest to largest. Another way we can talk about a relation other than a set of ordered pairs is with a diagram. Now we draw an arrow from the first set to the second set to denote that relation. So for instance, an arrow from 1 to 2 would be the ordered pair 1, 2. So this relation can be listed as f is equal to the ordered pair negative 2, 5, 1, 2, and 3, negative 1. Now remember, the domain is the set of first elements, or the x values, which would be negative 2, 1, and 3. The range are the y values, 5, 2, and negative 1. Now if we were going to plot the relation, all we do, and this is just back to our regular graphing, you'll notice in this problem each tick mark is 10. So that would be over one tick mark, up 35, 10, 20, 35. So we just put a dot there. Negative 580 would be up here to here. 40, 15 would be over to 40, up 1.5 dots, which would be 15. Negative 90, negative 20 would be down here. And 1070 would be right there. And we're just labeling those points on the graph. And that's one way we can write a relation. Another way to represent a relation could be the graph of a line or a curve. For instance, if it says let f represent a relation consisting of all ordered pairs having the form x, comma 2x. Well, what we do is we just pick some numbers. So if we pick x is 0, then the y would be 2 times 0, which is 0. If we pick x as 1, the y would be 2 times 1, which is 2. If we pick x as 2, 2 times 2 is 4. So we just randomly pick some over here for our graph, and what you're going to find out is the relation is actually every point on that line, not just those 5 points. For instance, if x is 1/2, 2 times 1/2 would be 1. That point is also included on your graph. It's not possible to go through and list every single one of these ordered pairs. So by not listing them, we can draw a graph to just represent all the ordered pairs. Now, let's go the other way. Let's say we've got the graph and we want to determine the domain and range for the graph. I'm going to switch colors so you can see me right on the graph. The domain, remember, these are the x values. So we could go through and say, well, this is the ordered pair negative 3, 0. This is the ordered pair 3, 0. This is the ordered pair 1, comma something. This is the ordered pair 0, comma 6. And we could do that for all these little points on the graph. This is the ordered pair 2, comma something. So the question is, if you listed out all these ordered pairs, what x values are included? Well, remember, it's not just 0, 1, 2. It's all of the ordered pairs between negative 3 and 3. So your domain would be the interval beginning at negative 3, ending at 3. Because no matter what number you pick in there, you would be able to go up or down on your graph and find the y value that matches up. Now the range, those are the y values. Well, your lowest y value is negative 6. Your highest y value is 6. And you also have every y value between negative 6 and 6 on there. So we say that the range would be negative 6 to 6. Second picture. they give us a graph. Now, if they would have put a dot on the end, then that means that graph would stop right there. We'll talk about this real quick. If we had two dots, then the domain would be all x values between -1 and 4, because this graph stops right here where x is -1. This x value stops where x is 4. Okay? But since they did not give us any points, then we assume that the graph goes on forever and ever and ever. So if we extended it all the way up, eventually we would include every x value on that number line. So the domain is all real numbers. Now the range, remember these are the y values. Your lowest y value is right here, which would be about -2.8. And all of the y values above that are included, so we would say that the range would be from -2.8 to infinity. Now, switch gears, let's talk about a function. A function is a type of a relation in which every x value corresponds to one and only one y value. Okay? A relation is any set of ordered pairs. A function is a special type of ordered pair in which every element in the domain corresponds to exactly one element in the range. Now, if x is any element in the domain, then x is called the independent variable, meaning it can move around, you can choose whatever you want. If y represents any element in the range, then y is called the dependent variable. And you can think about this as y will depend on the value of x that you choose. Okay, so if we've got this relation S, is this a function? If not, tell why not. Well, let's look at the x values. X -17, -10, -22, -12, and 11. For each of those x values, do we only have one y value for each one? Well, because all of the x values are different, then we say, yes, it is a function. What about this one? If S is the set of ordered pairs 13, 4, 14, 6, 26, 0, 12, 4, 13, 1, would that represent a function? Well, look at your domain. 13, 14, 26, 12, 13. Does every element in the domain go to one and only one y value? Well, you notice the first time x is 13, we get y is 4. But the second time x is 13, we get y is 1. So is that a function? No, it's not. Why not? Because the x value 13 corresponded to two different y values. Okay? Now, let's say we've got a function, or let's say we've got a graph, and we want to decide if that graph represents a function. Then we have the vertical line test, or you may refer to this as the pencil test. Okay, and what it says is, if every vertical line intersects a graph at no more than one point, then the graph represents a function. For instance, if we've got a graph and we can draw a vertical line everywhere on that graph, and we only intersect the graph in one spot, or at most one spot, then it is a function. For instance, here we did not hit the graph in more than one spot. Here we hit the graph in several spots. Therefore, this is not a function. Okay? Let's do a different graph. Let's say we've got one like this. Vertical line here, we hit it in one spot. Vertical line here, one spot. Vertical line here, one spot. Vertical line here, one spot. As long as you can do that all the way across and you touch the graph in only one spot, then we have a function. Okay, Let's try just a couple more. Let's say we've got this picture, and let's say we've got a parabola. Is that a function? Well, for every vertical line, do we hit the graph in at most one spot? Yes, 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 yes. So is this a function? Yes, it is. Okay, let's try another one. What about the parabola laying on its side? We're okay, we're okay. As soon as we draw a vertical line, any vertical line, and we hit the graph in at most one spot, then it's not a function. Okay. What about that? We're okay here, we're okay here, we're okay here, but there was one spot on the graph, or at least one spot on the graph, where we hit the graph in more than one function. So, in more than one spot. So, no, that is not a function. Okay. Now, what about if I give you an equation and ask you, is it a function? Well, remember, for every x value, there can only be one y value. So, what we want to do is we want to solve this equation for y equals. So we're going to say subtract x to the third, subtract x to the third, and we get y squared equals 4 minus x to the third. Well, if we're trying to solve for y, the square root property says, well, we can square root both sides, but we must also consider the positive and negative case of the other side. Then we get y is equal to the plus or minus the square root of 4 minus x to the third. Because for any x we choose, there are two y values. One's a positive number, one's a negative number. So that is not a function. For example, if we let x be 0, we'd get y equals plus or minus the square root of 4 minus 0 to the third. So y equals plus or minus the square root of 4. So y is equal to plus or minus the square root of 2. So that means if x is 0, y is 2. Also, if x is 0, y is negative 2, not a function. Okay, what about this one? X equals y to the third minus 9. Let's try and get it in y equals form. Plus 9 plus 9. So y cubed is equal to x plus 9. Now this time, to get y by itself, we're going to do the third root of both sides. Well, if we do the third root of both sides, we get y is equal to the third root of x plus 9. Doesn't matter what x is, there's always one answer for y, and it's the third root of x plus 9. So yes, this one is a function. Okay, try a couple more. I'll give you a hint. Anytime you see a y squared, and you know to get this y by itself, you're going to have to do plus or minus the square root. Not a function. Anytime you see a y to an odd power, it's going to be a function. We'd do minus x, negative 3y equals 9 minus x, divide by negative 3. So whatever x is, you do 9 minus that number, divide by 3, and that gives you the one y value. So yes, this one is a function. The y squared is not a function. What about ordered pairs? If we have negative 5, 4, negative 4, 4, and so on, look at that. This is sort of like the ordered pairs. Because all of the x values are different, we don't have to worry about the y values. This one is going to be a function. Okay? This is what we call a constant function because it doesn't matter what x is, y is always equal to the constant 4. Okay, we'll jump down to this one. This one, x is negative 2 here and x is negative 2 here. Normally when you see the same two x values, you say not a function. In this case, if x is 1, y is 1 here, and y is 1 here, that one actually is a function. Okay, that was sort of a typo. This is supposed to be -1. So if at that point we had that the x value is -2 and the y values are 1 and -1, then it's not a function because the x value of -2 has a y value of 1 and it has a y value of -1. Now, function notation, to say that y is a function of x means that each value of x from the domain will have exactly one value of y. Okay? And to emphasize that y is a function of x, or that y depends on x, we write y equals f of x. And I know it looks like f times x, but it really means f of x. F is the name of the function of the variable x. So, for all purposes, you just need to remember that f of x is simply another name for y. So this is the equivalence of saying y equals 2x minus 5. Find y when x is 3. And you take the 3 and plug it in. Function notation says, hey, f of x is 2x minus 5. F of 3 means go into your f formula. Everywhere you had an x, plug in 3. So f of 3 equals 2 times 3 minus 5. F of 3 is equal to 6 minus 5. F of 3 is equal to 1. Okay? F of -1 and f of x equals the square root of x plus 5. That means, hey, let x be -1. So f of -1 means the square root of -1 plus 5, which is equal to the square root of 4, which is equal to 2. Now, f of a plus b, given f of x is x squared plus 4, this one's going to require a little bit of algebra. F of a plus b means everywhere you had an x, we're plugging in a plus b. So we've got a plus b squared plus 4. Well, remember, a plus b squared means a plus b times a plus b. If we FOIL that out and simplify that, we'd get a squared plus ab plus ba plus b squared plus 4. And that's doing first, outer, inner, last, which gives us a squared plus 2ab if we combine ab plus ba plus b squared plus 4. And that would be our solution. Okay, on a graph, if we don't have a formula to plug into, same idea. Let me go back to ink. Okay, f of 0 means find the ordered pair on the point that has an x value of 0. Well, here's where x is 0. What's the y value for that ordered pair? 0. So f of 0 is equal to 0. What about f of 3? That means look on the graph to where x is 3, which is anywhere right here on this line. That's this ordered pair right here. So that's the ordered pair 3, 0, which means the y value for f of 3 would be 0. What about f of 4? That means look on your graph to where x is 4. Find the point on your graph which says, hey, the y value is 5. So f of 4 is 5. So what you want to remember is this is the x value, this is the y value, so the ordered pair 0, 0 is on the graph. X is 3. When x is 3, y is 0, so 3, 0 should be on the graph. If x is 4, y is 5, which means the ordered pair 4, 5 should be on the graph. Now, last thing is graphing. Sketch the graph of f by hand. We just need a couple of points to find the shape of that graph. So if we went through and said f of 0, that means we'll plug in x is 0. So that's 2 times 0 is 0. 0 plus 1 is 1. So that means 0, 1 is on the graph. Let's do another one. F of 1. 2 times 1 is 2. 2 plus 1 is 3. So that means the ordered pair 1, 3 is on the graph. Let's do another one. Let's just pick something. Let's say we pick f of 3. 2 times 3 plus 1, which is 6 plus 1, which is 7. So that means 3 7s on the line, on the graph. What about f of negative 2? 2 times negative 2 plus 1, which would be negative 4 plus 1, which is negative 3. So negative 2, negative 3 is on the graph. Let's see if we've got a pattern yet. Over 0 up 1, over 1 up 3, over 3, 1, 2, 3, 4, 5, 6, 7, over 3 up 7, negative 2, negative 3, back 2, down 3. You notice the pattern? This is what we call a linear function. The graph will always make a straight line. Now, if we want to do that on our calculator, okay, you just go to y equals on your calculator, enter 2x plus 1, press graph, and that would give us the graph, and we'll do some of those in the next video. Now you're ready to complete the homework from section 1.2 in my math lab.